Hello, so today we'd like to present our work on privacy-preserving inference on the edge. Always-on sensors are widespread in the everyday devices we all use, from smart speakers to home security cameras, and many more consumer products are expected to include always-on image or sound sensors as part of their operation. In spite of the usefulness of these devices, there's growing consumer concern over threats that can leak sensitive information. This turns out to be a dilemma for innovators, since there are a lot of important medical, environmental, and consumer products that would benefit from applying machine learning to sensor data, but have no interest in recording this raw sensor output. So the question is, how can we have privacy-preserving machine learning at the edge? The primary issue is that recording and storing raw sensitive data can expose unwanted personal insights. There are several possible ways that this unfiltered data can be revealed to malicious actors. First, security vulnerabilities are especially common in edge IoT devices, and combined with the fact that these edge devices are packed with sensors and often store a significant amount of data, it's no surprise that these devices are an enticing target for attackers. Next, consumers are concerned with devices recording them in detail, but not necessarily with sensors detecting less detailed information. And an application that uses data in a way that's acceptable and perceived as benign can be easily changed into something unacceptable through a simple software update. And finally, consumers of edge devices have limited insight into how sensor data is being used, which prevents them from being able to understand and trust the device. The real concern is with the recording of raw sensor data, and our solution uses a secure enclave to interface with the sensor, store raw sensor data, and run the machine learning model. And to the application in the non-secure world, we only present a binary output. For example, is a person detected? And this also allows us to rate limit the outputs from the secure enclave.
Now I'm going to talk about how we implemented this solution, starting with our hardware. So for these experiments, we used the Nordic NRF5340 PDK. It's based on an Arm Cotex-M-33 and has TrussZone support for Cortex-M architectures. The Nordic processor is connected to our camera module via a UART pass-through for the collected images. The Nordic is also connected to a host PC over UART. To provide a quick primer on TrussZone, it's a security extension for Arm that divides the processor into secure and non-secure states. It provides certain services such as random number generation, cryptographic acceleration via the cryptocell IP, and memory protection by its MPU. And in our case, we are primarily interested in the MPU. This is what enforces permission access to memory, which in turn enables us to create a sandbox for execution of untrusted code. In addition to instruction isolation, the MPU also isolates sensitive data from the non-secure state. The NRF has 1024 kilobytes of flash and 512 kilobytes of RAM that we partition via the linker. However, the permissions for flash and RAM are set at runtime by trusted code. Each security state must also have its own stack and handlers. And so trusted code must also set the virtual table offset, also known as the VTOR, at runtime. Transitions between these states are asymmetric and are generated at compile time. Transitions from the secure state to the non-secure state require a variant of the ARM branch instruction, namely the BXNS or BLXNS, seen in the diagram to the left. These variants check the security state of the target. Transitions from the non-secure state to secure state require secure gateways, or SG instructions. These are implemented by defining a non-secure callable region at runtime and then linking this said region for these SG instructions. Our trusted code handles peripheral interfaces, TrussZone setup, and initialization of the TF-Lite micro runtime. It is non-trivial, but we abstract this away from the application programmer via the API that we can expose. The application programmer has a much simplified view. They can request secure inference in a single call, and there is flexibility in defining the API that the non-secure world has access to. The example shows that non-secure code can request 3 image captures and get a binary output of whether we see a person or not. Any attempt to access the raw data in the secure image buffer will result in an exception.
On a relatively large person detection model, we show a very minimal overhead on the order of a few hundreds of thousands of cycles of execution time. In conclusion, we show a simple yet effective framework and abstraction that is capable of serving large models with minimum latency. For our next steps, we'd like to generalize this framework to other chips And we'd also like to include support for auditability and support software level protections such as stack canaries and red zones.
Can you comment on your software setup? Was there any OS involved?
Yeah, so this is just bare metal on the
Hello,
Hello, just bare metal, yeah.
Yeah, it was just bare metal.
Okay. What about if you want to update the ML model in the field?
Yeah, that's a good question. So I think ideally you would have some sort of like manager for the different models. So you could, just change a model by itself without, changing your application. So some sort of different part of the, I guess, higher level framework that allows you to manage the different models that you have.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being Arm. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. PRABHU Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Hymax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotg, and Synsets.